Okay, thanks a lot.
It's really a great joy and pleasure and honor to be here and to celebrate Noga's birthday. And let me move on. One beautiful idea of the organizers is to include in the poster for this conference 15 formulas which represent some of Noga's works. Of course, not every mathematical work can be represented by a punchline, a formula. And I was very proud when I saw it. About half of them I really could recognize. And then I announced a prize-winning contest on my blog for 10 shekels for everyone who will identify. The first one to identify each formula, which will be doubled if the person will actually come to collect it in person in the conference. And actually, all the formulas were identified, and I could just give a talk about these formulas, or about even each one of them. I will not go quickly about them, but really beautiful formula. Here are the people who won the prizes. The first one, for example, is separators for minor free graphs, extending the famous leap from Tarjan theorem. And then the almost solution to the Stanley-Wilf conjecture with the Ackermann function in exponent, all per shortest path, linear arboricity of graphs, the maximal number of directed Hamiltonian paths in tournaments is the famous, this formula number 5. Shannon capacity of the union, this is a very famous and amazing result. Shannon conjecture that the Shannon capacity of the union of two graphs is bounded by the sum of the Shannon capacities. And this formula, you can look at it, this is the sixth formula. You can see that we can have a graph and its complement of Shannon capacity is n, and then the union would be something like n to the power log n. So this proof, this conjecture. The Turan number for a symmetric bilateral graph. Here some of the winners of the prize not only found the formula, but also noticed a typo in the poster. And then the largest number of edges in a bilateral subgraph. So every graph with e edges have a bilateral graph with e over 2 edges, but you can make a sharper bound. And this is also a beautiful formula number 8. And then when we move further then now we go from down up. You can see the famous Alon Bocana formula. Leo Silberman identified the Ramsey number for C4, 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 and K8. I remember that this was discovered. This was in Oberwolfa 2000. You remember? We had this, the first of a series of Oberwolfa lecture conferences, and I think Vera Shosh asked this question, and I think Noga and Vojta sat down and they used this beautiful norm graph and other things, and they figure it out. Here is the formula. The third formula, Alon Newman, was already mentioned, and Alon, the two formulas in one, this is to save space. Oh, okay, sorry. The next one is again Alon Bocana. This is about monotone circuits. And the fifth one, this is a prize which was triples, because I promised to triple the prize for the first formula chronologically. This is from Noga's master, the maximum number of copies of H and the graph with edges, and there are some extensions by now, and so on. So these are the formulas for people who are eligible for the prizes. Please come to me to collect them. So Noga and I, we are academic twins. Here is a list of Micha Perez, student. I think it's out of memory, so maybe I missed some. So Kachalski, Michael Koren, Michael Kalai, the same name as me in Hebrew, were older brothers, not in Ideal. Also, our older brother, he was with us when we started, Ito Shemer. Noga and I, we did PhD precisely the same years. and then there are a list of further students, pupils that in the following year some students were joined of me and Mircha Perles. Ron Adino is a prominent researcher in advanced combinatorics and connectional strength theory. He came to be a graduate student, and he has a very remarkable record. Ron Adino has the second highest average grade among graduates of the Technion. Now, can you guess who was? Okay, so we were. Okay, so here is a. So I will tell you a small mathematical. Here is a problem that we thought about in the graduate years. Kupis and Mircha Perles, they asked the following. Suppose you have a configuration of points in the plane, is it always possible to find a line determined by the points, or contain two or more, so that there will be small difference between the two sides? The points on one side and smaller on points on the other side. So this is sort of a geometric, kernel-geometric disturbance problem, very nice problem. Kupis and Perles conjecture that you can always achieve a gap of 1 between the two sides. And then Noga found a very nice configuration that you can see here. I think on the spot that you need that the gap will be at least 2. And as far as I know, in the last 40 years, this lower bound was not improved. As far as the upper bound, there was a gradual improvement from square root n to log n to log n, which is the world record today by Ron Pinchasi. And it's still a very interesting open question if you can always achieve a bounded, if for every configuration of endpoints in the plane there is a line determined by the point, so that the gap between the two sides is bounded. Recently, Hagit had some new ideas about attacking this problem and promising. And so this is something which bothered us when we were graduate students. And we are twins, Noga and I, but we are not identical twins, unfortunately. And I always refer to Noga as my genius twin. But now I learned a new word, which is the word. Actually, about prizes, I should announce another prize, which is the best ever audience member in my lecture. It is Jennifer. Jennifer Chen is the best ever audience member in my lecture. We will see. We will. Actually, another prize. Today, when I entered this place, I saw a bunch of famous mathematicians from behind, and I could recognize most of them. Of course, listen, it's not a big deal to recognize from behind, but with the other people, I was very proud of myself. As time passed, at some soon I will not be able to recognize people from front, but from behind. Anyway, so I will post it on my blog, and I will let the audience try to identify this famous mathematician from behind. Let's see how it goes. Okay, so Polymath is a person whose expertise spans a significant number of different subject areas. Such a person is known to draw on complex bodies of knowledge to solve specific problems. And the idea of the Polymath was expressed by Leon Battista Alberti in the 1404-1472 in the statement most suitable to Noga, a man who can do all things if you will. Okay, so let's move. So I will tell you a little bit about my first collaborative paper with Noga, and this is a relator conjecture by Claude Berge. So this is also from the time of the graduate student. Every graduate years, every simple 4 regular graph contains a 3 regular subgraph. So what we proved is that every 4 regular graph plus an edge contains a 3 regular subgraph. And this follows from a more general theorem that a graph with n vertices and 2 n plus 1 edges contains a non-empty subgraph with all degrees 0 modulus 3. Of course, you know that every graph with n vertices and n edges contains a subgraph with all degrees are even, or even a cycle. but this is the result. The graph with n vertices and 2 n plus 1 edges contain a non-empty subgraph with all degrees 0 modulo 3. This is my first collaboration. So let me mention collaboration. So Noga is very high on my list of co-authors. We have 7 joint papers, and here is all the co-authors that have more than 2 papers with me. And for those with 2 joint papers, those with the star are actually people who had 1 paper and then after a period of time came back and worked on another paper. I'm very proud of that. And on the right, we can see Noga's co-authors. So I prepared this, so it might be incomplete. And I have, so on this list, I'm with Vera Sodi and Bela Bolobash, Paul Erdesh, Nati Lineal, Moni Naor, and Mario Segedi. And of course, many of these results. For example, Mario Segedi and Noga has famous papers about streaming algorithms that led to them getting the Gödel Prize. I'll mention something about Moni Naor later. So, what? These numbers should not be the same, right? I mean, on the right and the all the numbers are different. What? Well, the right list is based on the way Noga count. The left list is based on the way that I count the paper. Actually, so there is one joint paper with Larry Stockmeyer and Moti Ricklin that I counted twice because there was a conference proceeding and journal proceeding. You count differently when you have many papers. Actually, one thing I observed, you look at this graph, the numbers on the right are about 3 times the number on the left. Okay, what does it say about the overall papers? And you need some mathematical insight to realize that this is the area. It means that the number of overall paper is about 3 square times more, so like 9. Yeah. I hope to reach 100 papers in my career. I suppose this challenge Noga to reach 900 papers. So, okay. So here's a proof of this result. Every graph. Away from this because of the recording. Every graph with n vertices and 2 n plus 1 edges must contain a subgraph where the degrees are 0 modulo 3. So you look at you associate to every edge E of the graph a variable xe, and you consider 2 polynomials over the field with 3 elements, P and Q. So here are the polynomials. P is the product over all the vertices of the following expression: the sum over all the edges containing this vertex, xe square. All this sum you take again square and you subtract 1. This is P. And Q is simply the product of xe square minus 1 over all edges of the graph. So we have here 2 polynomials over the field with 3 elements. And if the theorem is false, then P minus Q is 0. And to see this, we consider, for every time we assign values to the variable, we consider the subgraph h of g described by the non-zero assignment. So for every assignment of the variables, we consider the subgraph which correspond to the non-zero assignment. Then when you take a non-zero number modulo 3 and you square it, you always get 1. So this means that for P, we look at the degree of every vertex, modulo 3, and then we sum it again, and we subtract 1. So this expression will be 0 if and only if the degree is 0. And the product will be 0 if and only if all the degrees the product will be non-zero if and only if all the degrees are 0. And in Q, the only way we can get a 0 the only way we can get a non-zero is if we take the empty, if all the xe are 0. And if the theorem is false, then we get precisely the same values. And therefore, if the theorem is false, then P minus Q is 0, but this is impossible because the degree of P is the degree of Q is 4n plus 2, and the degree of P is 4n, and there is a non-zero leading coefficient. So this is the proof. And the theorem, well, this is a short proof, but there is even shorter proof of the theorem. You can apply more directly a well-known result by Chevalier-Morning, and even more directly a theorem of Olson, additive number theory. But what we did in the paper, we played both with the method to get similar results, and also with the theorem to get some graph-theoretic consequence. And this was our 84 paper. And I should mention some other results, Tashkinov proof. Actually, Tashkinov proof is just ordinary graph-theoretic method about the same time, the actual conjecture that every 4 regular graph contains 3 regular subgraph. Redden and Semeredy proved that the graph is n vertices and Cn log n edges, always contains 3 regular subgraph. And they found, quite amazingly, they found the construction of graphs with Cn log n edges without this regular subgraph. And there are some interesting problems. For example, I still don't know if you insist that the subgraph will be of type 1, so it will be also 3-edge colorable. Can you still prove these theorems? I don't know that. Another very interesting question, is there a polynomial time to find a subgraph with all degrees divisible by 3 and a graph with n vertices and 2n plus 1 edges? So this is a very interesting question. How many edges guarantee a 3 regular subgraph? So can you, in the works of Semeredy and Redel, can you improve either the lower bound or the upper bound? What? And again also for the lower bound. Oh, I'm sorry. Yeah, I knew that. Sorry. So Laszlo Piver proved the upper bound and they proved the lower bound. Yeah, I remember something was there. Okay. I also apologize for all the accents and this over the names. I don't put them. And okay, yeah. So, but I think there is still a gap between n log n and n log n, right? Okay, yeah, it's Piver. Yeah, I knew that. Good. I will recognize Laszlo Piver from behind. I promise you. But this is a problem. Okay, here is another. So then we actually, although we were twins, we didn't meet so much in graduate school. I was in Jerusalem, and Noga was in the army. Then we were together as postdocs in MIT. And here is something we did. We found a new proof of the upper bound theorem for convex polytopes. Yeah, so it's, I don't know. So, actually, it's Alex Lubotsky. He's calling me, right? Okay, so, I should put him on speaker. Okay, so we gave a new proof of McMullen upper bound theorem for polytopes. It's the maximum number of vertices of the polytope with n facets. McMullen proved it for polytopes. It applied to a large class of shellable complexes, but not to all shellable complexes. And then there were two proofs by Kim Kleinschmidt and by Noga and me that applied to all shellable complexes. And our proof was especially simple. And also, famously, Stanley in 75 already proved the result for all triangulated spheres. And I should say, there are two major developments even further. Isabella Novick proved the upper bound theorem for triangulated manifolds, and Uli Wagner found a very beautiful result about extension of the upper bound theorem for arrangements of hyperplanes. And the nice thing about Uli's proof is that he actually used our method. And our method, for many years I was annoyed because on the level of H vector, which is some finer parameter, we proved something weaker than all the other. And this really annoyed me, but it turns out that for arrangement, this weaker thing is, you cannot go beyond it. And so our proof was actually useful. So, here is some pictures from our postdoctoral time. Here on the top right, you see the problem is I cannot walk. But then they don't hear me. Okay, so here you can see Noga Mazi, my wife, Neta, and Nurit, and Mili, in 84. Here is Neta and Mili, at the same time. Here is Noga and my son, when he was 8 days old. Actually, here's a picture of Neta and Abigail, so please ask also, we need to know what was supposed to. So we had a good time, many friends in Boston. And here are a few places where our roads crossed again. So again for the Boston Times, Goodman and Pollack and Dr. Gerard Noga proved that there are few polytopes. And I complemented this result by showing that there is a large number of triangular spheres, and as a consequence, we now know that there are huge gap between the number of triangulation of spheres and the number of polytopes. We have perhaps the main joint body of works is on transversal theorems. So we have two papers, one together from 95 and one with also with Ilka Matushak and Roy Mishulam, where we, based on the famous solution of Noga with Kleitman to the Heidegger, the Brunner conjecture, and we extend it further in various directions. So, of course, Noga is very famous for his works on spectral methods, many aspects of spectral methods of graphs. I was concentrated on working on the spectral properties of single graph, the discrete cube. We were both influenced by a work by Michael Ben-Or and Nati Lineal on collective point flipping. In this work, they posed two questions, and Nati, Jeff Kahn, and me solved one of the questions, and Noga and Moni Naor solved the other question. We have a joint paper about mobile user tracking and distributed job scheduling, or two papers, if I count it. Although I don't know what is mobile user tracking. I don't know. And social choice, we thought, both of us separately thought about questions, combinatorial questions coming from social choice. And we have some work regarding hereditary discrepancy of homogeneous arithmetic progression. So this is a little bit related to Terry Tau lecture tomorrow. Okay, another joint thing we did together is to organize a conference in 1993 in Jerusalem. This is the biggest conference I ever organized. It had about 200 or 250 participants, about 70 speakers, 30 plenary speakers. So the organizers were Noga Alon, Ellen Barcelona, Anders Bjorner, myself, and Elmad Biglerson. Of course, Noga continued he was the organizer of the Madrid 2006 ICM. So there were even more participants. One thing which was extraordinary about this conference is that among the 30 plenary speakers, there were 16 women speakers. So Polymath. So actually, there is a modern use to the word Polymath. Polymath projects are forms of open internet collaboration aimed towards a major mathematical goal, usually to settle a major mathematical problem. Actually, I didn't know that there is. So this concept was developed in 2009 by Tim Gowers, who described it as a large collaboration in which no single person has to work all the time, which is a very appealing feature. And it is in line with other forms of open internet research activity, which includes mass overflow and are sometimes referred to as science 2.0. And I think there is a quote from Nature that tells sometimes it's not market forces that achieve efficiencies, but cooperative. In any case, this is a very nice concept. I didn't know that the word, I thought that the team also invented the word polymath, but then later I found that it has another use. And in 2000, and here is a list of Polymath projects since 2009. There were 10 projects altogether. I think 7 of them went off the ground, and 3 were successful, at least in some sense. The first one was on Tim Dower's blog, and it was finding a new proof for more effective bounds for the density hedge conjecture. This was an amazing success. After I was quite skeptical, but I like the idea that nobody has to work too hard. But I thought nothing will come out of it. But amazingly, after 6 weeks, it led to success. Then there was Polymath 3, which was it's actually chronologically Polymath 4 came before. This was a notoriously difficult problem to find deterministically primes, but it was very interesting discussion. This was ran by Terry Cow. Then I tried to do a Polymath project on the polynomial Hirsch conjecture. Polymath 5 was about the Earth discrepancy problem. It didn't lead to the solution of the problem, but some ingredients of it were used in the recent solution of the problem by Terry Cow. You will hear about it. There was Polymath 7 about hotspots, some problem in differential equations. There was Polymath 8, which was successful to improve the results about gaps in primes. So the first part was to improve the result by Zahn, and then there was a gap between two Polymath projects where there were some new result by Maynard and by Terry Cow, and this led to a second phase of the Polymath to improve those results. And right now there is a Polymath 10 running on my blog about the sunflower conjecture, which I'll tell you a little bit about. And there's a few dozen Polymath proposals that were made. And in 2010 there was a debate organized by the Institute of Advanced Studies about Polymath. I will not read everything, but the main debater was Tim Gowers and Peter Sarnak, where Tim said that the Polymath could be a better way of doing mathematics, and Peter roughly said that the Polymath, although it can be used some endgame mathematical problem, it can be damaging to doing mathematics. And I was also invited to the debate, and since these two opinions were already taken, I had to find some other opinions. I opined that there's no hope and no danger that this can supersede the usual way to do mathematics. And Noga was also there, and actually a few of you also. This was nice. There were a lot of businessmen, and this was supposed to. I don't know if there were some contributions to the Institute coming from this, but in any case, and Noga said that it's interesting, but it runs the danger of making us managers rather than researchers, just moving ideas from one person to the other. And the Hebrew word for managers is maybe machers, which came to the news recently. Actually, I like, so I'm quite. There is one place where I acted as a macher, which I'm fairly proud about, also from the postdoc years. One day, Alex Lubotsky phoned me, not in the middle of the lecture, but he said, I have a problem. I work with Sarnak and Phillips, we have some problems of combinatorial nature. No, when people ask you problem of combinatorial nature or problem of combinatorial, it's a problem they cannot solve, and you don't see anything related to anything. But in this case, he asked me about eigenvalues and graphs and so on, and I knew a little bit about it, but the best advice I could tell him is to talk to Noga. And I think this was very fruitful. Okay, so Polymath 10. So let me tell you a little bit about Polymath 10. And this is the Erdős-Ragó sunflower conjecture. And the collection of sets is a sunflower if every element which is included in two sets is included in all of them. Okay, so is it clear we have a collection of sets? And it's a sunflower if every element either it's included in no set, or it's included in one set, or it's included in all the sets. So every collection of two sets is a sunflower. But when you have three or more sets, it's a fairly restrictive condition, and the sets are called petals. Petals. What? Okay. Petals, and the intersection is called the head. And Okay, I didn't tell you what the conjecture is, but I can also tell you the early heroes of the sunflower conjecture are Abbott, Hanson, and Sauer, Spencer, and Kostochka. Kostochka has the world record about the problem. I'll in a minute. It's a very nice paper. Actually, I heard recently a very sad story that there was a really prominent graduate student who did, I will not mention any name, but he did a really terrific work in his graduate. Then he went to a very nice place to do intern, and he was assigned to read Kostochka paper and improve it. And then he left mathematics altogether. Okay, so here's the conjecture. Let FKR denotes the maximum size of family of K-set without the sunflower of size R. And Erdos and Rado conjecture that FKR is smaller than some constant depending on R to the power of K. So it's only exponential. It's not entirely obvious that this is bounded by a finite number, but this is not easy to prove by induction. In fact, they prove K factorials times R minus 1 to the power of K. I said not easy? No. I meant not. Yeah, there is a Z2 transformation of everything I said. But yeah, I meant no. It's not hard. It's fairly easy. Okay, so this is the conjecture. It's a very nice conjecture, very nice mathematical conjecture. It's related to many things. Not yeah, both the theorem and it's really it's one of the things that it's not so good to be 60, but I think it's not bad to be 60. To do combinatorics all your life, and this gave us a lot of we can spend a lot of time on this. Anyway, so here is a family is balanced. If a family of K set is balanced, we can color the ground set with K colors so that every set is colored. We can ask the analog question for balanced family. Let's FBKR denotes the maximum size of a family of K set without a sunflower of size R. And there is a very simple lemma which says that FKR is smaller than e to the k than FBKR. So it's enough to prove the Erdős-Rado conjecture for balanced family. Of a balance, yeah, this should be balanced. Yes. And actually this is related to one of Noga formula. So for graphs, this says that every graph contains a bipartite graph of half the number of edges, and there is a formula by Noga to find a very delicate form of this. And here is we have the same phenomena, but not half, but I don't know, k to the k divided by k factorial divided by k to the k. And it would be nice to extend Noga result from formula number 8 to hypergraph. I don't know if this was done. In any case, we see that there is only exponential gap between the problem for general families and the problem for... Okay, so one thing one can consider is the following refinement. Let F, K, R, and M be the maximum number of K subsets from N without a sunflower with R petals whose head has less than M elements. So this question is already interesting for the case where R is equal to 2, and for the special case with R equal to 2 and arbitrary M, and for M equal 1 and arbitrary R, we get well-known questions of Erdős-Rado type. Very, very important, interesting question. And we wanted, in the project, Polymath, we wanted to consider them. So now let me tell you briefly one approach. This is the approach I proposed. There were other approaches in this project. I looked at Polymath 1, tried to see what we can mimic. And one nice thing about Polymath 1, there was a proposed approach in the beginning to start with. So we could deviate from it, but this was a nice way to start. So I thought, okay, let me mimic this way. So here is so let F be a family of sets, and let K be a simplicial complex spanned by F, and let HI of K be the ith reduced homology group of K. So here is So here is how you define homology. Let me remind you. If you have a simplicial complex on a vertex set, you define the space of chains as a vector space spanned by faces of dimension K. So this is the vector space spanned by faces of dimension K or set of dimension K plus 1. And then you look at the boundary operator. The boundary operator is the alternate sum of for a set of size k. The boundary of a set of size, of a face of dimension k is the alternate sum of faces of dimension k minus 1. And this is the definition. And once you know this definition, it's very easy to define the homology group. You define the space of cycles, which are all the chains that the boundary is 0. The space of boundaries is all the image of the boundary of chains from one higher dimension, and the quotient of these two spaces is the homology. So if you never saw this, it's a little bit quick, but this is the way homology, simplicial homology is defined, and it's quite nice that this definition held from time to time application to combinatorics. And here is a variant. Instead of looking at the boundary operator, you can add weights, where we saw already. Adding weights is a nice trick, and you can add weights. So when you look at subsets of size k, then you add a weight which is w of the index u. So every time in the boundary, you always delete one vertex, and you add weight which correspond to this vertex. So this is the weighted version of the notion of simplicial homology. And if you think about it, at least over a field, there is a simple scaling property between the matrix defining homology and the matrix defining weighted homology, which tell you that the homology spaces, vector spaces, are the same. So adding weights, at least as long as there are non-zero weights, does not change the homology. So why is this idea, how could this idea be useful? The reason it could be useful because once you introduce weights, you can look at different weights, a boundary operator with respect to different weights. And here is now let's define the notion of cycle. So a simplicial complex, so a cycle of the form 2-1 are those k-dimensional chains which vanishes for two weights. For one weight partial 1 and one boundary operator, for two boundary operators. One boundary operator partial 1 and one boundary operation partial 2. And more generally, we can talk about those k-dimensional chains which vanish when we apply successively C out of B boundary operators. So this gives us a larger class of homology type invariants, which that can be useful for combinatorial purposes. You know, the main property of simplicial homology is homotopy invariant. This is not preserved, but these more general notions are related to combinatorial properties. They are also related to the notion of stresses that Latsi talked. So here is, I define what are cycles, but here is the definition of homology. So here is the homology with parameter 2 and 1, and the homology is the quotient between the space of cycles and the space of boundaries, where the cycles are those elements which vanish after applying each one of two boundary operators, and the boundaries are the images under one boundary operator of those cycles which vanishes when you apply successively two boundaries. And so this gives you a new type of homology. Okay, and then the program I propose for this sunflower is to prove these two conjectures. The first conjecture is that if you have a balanced family of k-sets without a sunflower, then these modified homology groups for all the links will be 0. And for this conjecture, there were some partial results available. I'll mention them in a minute. And then there was a second conjecture. We said that if you have all these local properties, then there is some global homology which vanishes for the whole simulation. And if these two conjectures are true, now the second conjecture was inspired by some analogous results, but for ordinary homology, but as it is, it was largely a wishful thinking. And if both conjectures are true, then this will settle the Erdős-Sunflower conjecture with fairly small constant. And even you can negotiate on conjecture A, you find the weaker statement. So I'll tell you in a minute what happened. I mean, And here are some more news from Polymath 10. So here I played the role of a manager or a master, and I tell you something that happened. So perhaps the most significant development was by Philip Dick. I don't know him personally, but he found a better connection between the balance and the general case. If the sunflower conjecture is true, then the bound for general families is only 1 plus law of 1 to the power of k times the bound for balance. So this is a very nice construction, and you can think about it also negatively. All you need to disprove the conjecture is to find a way to show that the answer for non-balance is larger by 1 plus epsilon to the k than the answer for balance. So if you find a complementary construction of this nature, then the two constructions will disprove the Erdős-Rado. So this is very nice. So Domoto Palvogli, he showed down various working conjectures that I proposed and raised interesting questions. In particular, yesterday he raised another approach to the whole conjecture. And this time I add all the accent because this is really remarkable. Over all the 3 O's. Some computer experiment was made by several participants. Tim Gowers proposed a pseudo-random approach. Shachar Lovet's comment on special case related to matrix multiplication. Ferdinand Hieringer found inequalities for the refined. Is Ferdinand here? Oh, he's here. Oh, hi. Yeah. So for the refined version. Eran Nevo showed that the balanced family in section implies a cyclic, and the exchange of this result are push over the partial result towards conjecture A, but it also leads to some other partial results. Erdős-Corrado result for balanced families. Karima Di Paradiso discussed the Cohen-Macaulay case, and some new extremal results for balanced families were found. So this is very nice. After I prepared this guy, there was another development. So this conjecture, which was a wishful thinking, it turned out to be false. So this moves us back to the drawing table. At least as far as my original idea of using this irritated homology is concerned. I should tell you, when you work alone, one way you do in such a situation, you become obsessive about the problem, and it's very hard if you administer such a large scale, or if not large scale project openly and publicly. It's not clear how you can be obsessed and you have some responsibility. Anyway, so we will see how things develop. Will develop. So we can ask. In any case, you are all welcome to look at my blog at the Polymath 10 and contribute some new ideas how to attack the general question or some special case of it. And of course, you are welcome to read the classic paper by Joel and by Kostochka. But don't be alarmed. Don't move away from mathematics. Our Polymath project and more generally the Science 2.0 viable idea. So we can this question we can first we can put aside all the question about incentives, and we can ask, even in the ideal world, can it really generally lead to a better way of doing science? At least in some special case or to other major fruits. And the other question we can ask is, what about incentives? So of course I don't have any answer to this question. We can experiment and we can try this idea. But I should say that this is a little bit related to an area which, I don't know, someone postdoc and I did some work, which is social choice. Question about aggregating information and preferences of many individuals. So I don't know how... Yeah, so this is a nice... So I think... Okay, yeah. Thank you, Jennifer. Yeah. So let me end by mentioning a very nice, very beautiful result of Noga in social choice theory. I think it should be better be known by professionals in social choice. And this is the following question. Given a committee of K members, K is not integer, that need to give, you have a committee of K members that need to give M fellowships. So you have unlimited number of applications, but you can give M fellowship. And you want to have, and you want to vote on each, you want to vote by majority, whether to prefer one, and you want to find a rule so that will exclude the possibility that the candidate will not get the fellowship in spite having the majority of the committee preferring her to all those who received the fellowship. So how can you find such a rule? This is the question. And if you, okay, if there is only one member of the committee, no problem. Yeah? If you have a famous theorem of Condorcet, here is a picture of the sculpture of Condorcet, is that you cannot do this if you give one fellowship and you have 3 committee members. If you have 3 committee members, no matter how you do it, there are situations where there will be one guy who didn't get the fellowship that majority of committee members prefer on the one who got the fellowship. What Alon, Brightwell, Kirstein, Kustochka, and Winkler prove that we cannot achieve this if n is smaller than ck divided by log k. But perhaps even more remarkably, they show that we can achieve it if m is bigger than c times k times log k. So if you have enough fellowship, given the committee size, if you have enough fellowship, you can choose the recipient so that nobody who is not chosen is preferred by the majority of the committee members. This is a very beautiful theorem. And we can ask what about the general voting rules of the majority, and let me not. Yeah, as far as I know. At least, yeah. Last time I asked, no, this was two weeks ago. No, I think maybe one should conjecture K, right? So, happy birthday, dear Noga. A few more pictures, and some of them you already saw.